Let's just go over a few examples. Example. Let me bring. It's easy to draw, but since I have it, why not? So it's pretty simple. It's a frame, hopefully, from what I see. It's a frame. We have force P applied to member BC, and then we have a couple M applied to member AB. Dimensions are not given because we are not trying to find unknowns here. What we are asked to do is, for the frame, draw the free body diagram. Free body diagram of part A. It says each member, and part B it says two members connected together. All right, so I have this frame, right? Now it is definitely a frame. It's not a truss because I have force P applied in the middle of member BC. So already we have a multi-force member. And also there is a moment M. That also creates a multi-force member because AB is not going to be a two-force member anymore. That moment also is applied to member AB. So let's start with part A and draw free body diagram for each member. Let me use a thicker line. Let's say this is member A, B, and call it B. So what should I put there? All right, I'm taking this away or dismantling this whole frame. I'm just looking at member AB. Right? I want to draw the free body diagram for member AB. What do you see that I have to put there? What is there that needs to be taken into account when I'm looking at this free body diagram? Give me some suggestions. Pin support, yeah, A is a pin, so I have to take that into account. Moment M, exactly. So pin support, there you go. I'll just put it, let's say go with positive direction. This is pin, this is pin. Let's call this, I don't need red anymore, so let's call this AY, AX. We have the moment. I can put it anywhere, right? Moment, keep in mind, moment is a free vector. Can go anywhere. I'll just put it here. And couple, I meant, sorry, I misspoke. Moment, well, it could be also, it's a moment of a couple. All right, and what else? So far, we have, we taken into account, imagine, again, remember that we're taking this out of this whole frame. We're taking into account, we're isolating this. We're isolating this member right there. We isolate that following the procedure. Now we should start, we should put all the internal external forces. I put AX and AY because I removed the support, so support reaction is there. I put the moment, which is some external, the connection there. Right? Member AB is connected to member BC. So once we have a connection, I have FBC, yes, I need to take into account some force applied to this member from BC because they're connected. Right? If they're connected and this is a frame, definitely there will be some force between them. Right? It's an internal force. Think about what we were doing when we were using method of joint. Right? Anytime we're looking at a joint, we had to put all the forces applied to that joint on our free body diagram for that joint. Now, think about this as a joint, but is attached to B. Right? This is right there. So what I need to do, I have to take into account the force applied to B. Now, if I didn't have this moment, if M was not there, this would have been a two-force member. And I could just easily say, well, if this is AB, this is A, FA, this is FB. It's a two-force member. There could only be two forces, and they both should be along the member. Now, because of this moment there, now this is not the two-force member. That moment messes things up for me. So at this point, I don't know the direction of FB anymore. So all I have to do is just do the same thing that I did for the joint and the support. I have to just consider two forces, one in Y direction, one in X direction. Should be X. One in X direction. Right. If it was a two-force member and I didn't have that M, great, I could just do what I did here. But unfortunately, we're not that lucky, right? In terms of this member. This doesn't work because I have that moment there. So I end up not knowing the direction of A and the direction of B because there are more than just two forces in this member. As a result, when we don't know the direction of a force, we just have to put two components saying that, well, we don't know the direction. So there should be two forces there, at least two components of the force. And that's pretty much the free body diagram for this member. All right. Let's look at the other member. Let's look at BC. Let's draw it here. All right, so what forces I have to put there? This is B, and this is C. What is there that I have to take into account? CY, CX, exactly. These are the obvious ones, right? We have a pin support, CY, CX. So this is CX, this is CY. I have force P, it's an external force, so obviously I have to put it there, wherever that P is applied. I'm not given the dimension, so I'll just put it here. Now we go to point B again. Now keep in mind that I'm isolating BC. All right, I'm isolating BC. When I isolate this, well, I took into account the removed support. I took into account the external force P. I have to take into account the internal forces, the interaction between members. Right? Since this is separated, I have to compensate for whatever force that was applied from AB, member AB to member BC. Now, how do I compensate for that? Well, if I took the direction of BX, look at the previous free body diagram. If I took the direction of BX to the left, I have to put the BX on this one to the right. Why this is the case? Because of Newton's third law. Right? At point B, the structure, the frame is not falling apart, is not dismantling, right? It's just holding, it's just standing there right there. That means it's in static equilibrium. So whatever force is applied from member AB to member BC is equal to the force applied from member BC to member AB. Right? Action and reaction. I don't know what is the direction of this force, but since I decompose that force at B to BX and BY, I have to put the forces in opposite direction on the other member. Again, Newton's third law. Any force that we have, since we're in equilibrium anywhere, any force we have on the other member, we should flip and put the opposite force with the same magnitude in the member that is in contact with it. So that gives me this one, BX. That's a very ugly or vertical one. BY. They have the same magnitude as BX and BY on the other member, but in opposite direction. All right, so that's the difference, right? You start, that's the procedure. You start looking, you isolate each part, draw the free body diagram for that part, but you have to take into account remove supports, you have to take into account for external forces and couples, and you have to take into account for internal forces, the forces that are there within the structure that you don't see in a normal situation, like by looking at the total structure, in this case a frame. Like at point B, there is no force applied, but there is an interaction between these two members. So there is some force applied from BC to AB and some force applied to AB to BC. Those forces could be zero when you do the analysis, but the assumption is there is some force. So you have to take them into account. Once I take them into account on one member, remember on the other member, at the point of action, at the point of contact, forces should be in opposite direction, same magnitude. Because they're in equilibrium, and whatever force is applied to this one is equal to the force applied to the other one. Well, technically, it doesn't have to be in equilibrium either. This is just Newton's third law, right? Whenever you have force applied, it's similar to smooth contact, if you think about it, or any support reaction. Whatever force applied to one member, the same amount of force applied to that member from the other member, at wherever they're in contact. All right, part B. Any question about this one? All right, we'll do more practice, but two members connected together. So let's do that. Here, there's here, and there one. There was the other one. So that would be B. This is A, and this is C. So what are the forces on this? I'm drawing the free body diagram now, not for each member. Instead of isolating each member, I'm drawing the free body diagram for the whole structure, right? Isolating this whole frame. Right, so I have external forces. I have one P applied here. Right. I have the moment there. C, exactly, and then P. Yeah, I put P there. C also is a support. I'm removing the support because I'm isolating the frame, so I have to put CX, CY, and then the same story at A. AY, AX. Direction. So that's the free body diagram for both members connected together, or the whole frame, if you want to think about it.